In this final lecture of the course, we will be proving the Little Picard's theorem. The Little Picard's theorem tells us that if you have an entire function which is non-constant, then it cannot omit 2 points. We have developed all the machinery needed to prove the theorem, but we will first give a characterization of functions which holomorphic functions defined on a simply connected domain which omits 2 points. Let me state down the proposition. We will see how this is going to be used while we prove the Picard's theorem. So let's start with a domain omega which is open connected and which is simply connected. Let omega be an open connected subset of C which is simply connected. And suppose f is a function on omega which misses the 2 points 0 and 1 very specifically, which omits 0 and 1. That means that f inverse of 0 is empty, f inverse of 1 is empty. That's precisely what it means. The conclusion is that then there exists a holomorphic function g on omega such that f of z is equal to minus of the exp of pi I times cos h of 2g of z. Let's give a proof of this. The moment it omits 2 points, we are forced to have some function g such that f can be written in this manner. Let's see why that is the case. The first observation is that if you consider C to C star, the exponential map, this is a covering map which we have already noticed, and f is now a map from omega to C star. Now, omega being open set is also locally connected, and hence open connected, locally connected, simply connected, all this is satisfied. There exists a lift. Let's call that lift f tilde. We don't have to care about the uniqueness part here. One lift should work. So let f tilde be a holomorphic map, holomorphic function on omega such that x of f tilde of z, this is equal to f of z. From this f tilde, let's define a new function. Define capital F of z to be equal to f tilde of z by 2 pi I. The reason why this capital F is being defined in such a manner is because if capital F takes integer values, so notice that if capital F of z is equal to n, then what do we have about f of, say, z naught? Suppose f z naught is a point so that capital F of z naught is n, then f of z naught is going to be equal to exp of f tilde of z naught, which is going to be equal to the exp of 2 pi I n for some integer n, which is equal to 1. But notice that f omits the value 1. So this cannot happen, which is a contradiction. And what does that mean? That means that f, capital F, does not take integer values. The integers do not belong to the image. So in particular, we have now two maps. We have a map from C star to C star given by z square, z going to z square, that's a covering map, and we have omega to C star given by capital F. Notice that f doesn't take integer values, in particular f doesn't take the value 0, f doesn't take the value 0, and we have a lift which I am going to denote by square root of f. It's actually the branch of the square root function. We also have the following map, C star to C star, again z square, and look at f of z minus 1. This also is a map into C star, because f doesn't take any integer values. In particular, it's not going to take the value 1 either, and therefore we have a lift here. This is going to be square root of f of z minus 1, right? We do have now two holomorphic functions, which is given by square root of f and square root of f minus 1. Let's define the function h of z to be equal to square root of f of z plus 1, or maybe I should be a little more careful, square root of f of z minus square root of f of z minus 1. The first observation is that h does not have 0 in its image. H of z is not equal to 0 for z in omega. Remember that h is a function from omega into c. In fact, I am saying that it's into c star, because if h of z is equal to 0 for some z, then it means that f of z would be equal to f of z minus 1, which is a contradiction, and therefore that's never going to happen. I'm going to again consider the covering map exponential, which is from c to c star, and look at the map h now from omega into c star. We are again in a perfect setup to lift our function. We are effectively taking branches. If you are more comfortable with that language, this is a branch of the logarithm that we are actually considering. Let's call this lift g. i.e. exp of g of z, this is equal to h of z. Now let's see what happens to cos h of 2g of z. That's what we are interested in right now. We will rather look at this plus 1. If you go up and look at the statement, it was cos h of 2g of z times pi I that we are interested in, isn't it? So let's look at cos h of 2g of z plus 1. What is this going to be equal to? By very definition, this is going to be equal to e to the power 2 times g of z plus e to the power minus 2 times g of z by 2 plus 1. That's the very definition of cos h, right? And if you notice, this is just e to the power g of z plus e to the power minus of g of z, the whole square by 2. If you expand it out, that's going to be the same thing above. And we know what e to the power g of z is. E to the power g of z is exactly equal to h, because after all g was the lift of h, right? It's a branch of the logarithm of h. So this is going to be equal to h of z plus 1 by h of z, the whole square by 2. But what was h of z? H of z was square root of, let me just write it down here, h of z was equal to square root of f of z minus square root of f of z minus 1. So what is 1 by h of z? Should sit down and check that. This is just going to be equal to square root of f of z plus square root of f of z minus 1. Just multiply in the numerator and denominator by square root of f of z plus square root of f of z minus 1, you will get this. And therefore, if you add it up, you are going to end up with 2 times f of z, right? So we have cos 2g z plus 1 is equal to 2 times f of z. But what do we know about e to the power 2 pi I times f of z? Let me just go up and remind you what our capital F was. Capital F was this: 2 pi I times f of z is f tilde of z, and by very definition, this is equal to, let me write it down here, e to the power 2 pi I f of z is the same as e to the power f tilde of z, and f tilde was a lift of f, so it's a branch of the logarithm of f. So this is going to give you f of z back. And what is it to the right? You multiply now, this is just going to be equal to, what was all this? This is cos, let me write down what it was here. This is cos h 2g of z plus 1. So this is cos h 2g of z plus 1. So if you multiply by pi I and lift it, take the power, this is going to be equal to e to the power pi I times cos h of 2g of z times e to the power pi I, which is minus 1, which is hence equal to minus of e to the power pi I cos h of 2g of z. And that is precisely what we were trying to prove. So we have now got a function g which is defined on the domain omega, which is a simply connected domain, which satisfies the condition f of z is equal to minus of the exp of pi I times cos h of 2g of z. So why did we deal with such a weird function g? The reason is that this g is special. It tells us, we will just see in the next proposition that g is a function which does not contain a disk of radius 1, any disk of radius 1 in its image. Let me write down the proposition and then we will prove it. The function g does not contain any disk, a disk or any disk of radius 1 in its image. So if you have a disk D whose radius is greater than or equal to 1, then D cannot be contained in G of omega. That is precisely what the proposition says. Let's see why that is the case. The first claim here is that G does not intersect any points on the following set. G of omega does not intersect points in the set capital S, which is given by plus or minus log of root n plus square root of n minus 1 plus half of I m pi, where n is greater than or equal to 1, positive integers, and m belongs to integers, any set of integers. The first thing to note is that if I have to capture the set here on the complex plane, they are just going to be a complex, they are going to be a grid of this sort with the points on the vertices. They are going to be exactly these points. This is what the points which are being darkened will be the points of capital S in this case. Now let's see what is the, assume that this claim is true. Let's assume for a moment that the claim is true, and let's see why this is going to give us a contradiction. Assume that why not contradiction, why this is going to give us the proposition. Assume that the claim is true. The first observation is that if you pick any, if you pick the diagonal of any such rectangle here, we can bound them above. Why is that the case? Length and the breadth can be bounded in each of the rectangles given here. The length is going to be bounded by, or the height is going to be bounded by the, let me write it, the height of each rectangle is bounded by half of I times m plus 1 pi minus half of I times m pi, the absolute value, which is equal to pi by 2, which is in fact less than square root of 3. This is something which you should sit down and check. And what about the other width? This is the height. Let's look at the width. Log of square root of n plus 1 plus square root of n minus log of square root of n plus square root of n minus 1. This is what we are interested in. So plus or minus is there, but we are looking at the absolute value. So what is going to be the absolute value here? The first observation should be that this is indeed greater than 0. The length is going to be greater than 0, and that's not what we need. We need an upper bound. To check that this is indeed an upper bound, let's look at the function log of square root of x plus 1 plus square root of x minus log of square root of x plus square root of x minus 1. And if you consider this function, let's call it something phi of x, this is a decreasing function. Check that phi is a decreasing function. Some real analysis checks to be done, which I will leave it to you. Check that phi is a decreasing function and phi of 1 is less than 1. Phi of 1 is just going to be equal to log of root 2 plus 1, which is less than log of e, which is 1. So this is certainly less than 1, and because it's a decreasing function, we have absolute value of log of square root of n plus 1 plus square root of n minus log of square root of n plus n minus 1. This is less than 1. So the height and the width both are bounded by root 3 and 1 respectively. Hence the diagonal of every rectangle, this is bounded by root 3 square plus 1, the root of that, which is equal to 2. And therefore, if you consider any circle of any disk of radius 1, its diagonal will have distance or length equal to 2, and therefore it will have to intersect some point in the grid that we just have. Hence, any disk of radius 1 intersects some point in S. So if we prove indeed that g of omega does not intersect this set S, we are done. We have our result. So let's now try to see what happens if g of omega does intersect. Let z0 be some point in omega such that g of z0 is equal to plus or minus log of square root of n plus square root of n minus 1 plus half m I pi. We know that f of z is equal to minus of exponential of I pi times cos h 2g of z. Let's see what happens to cos h 2g of z. Let's first focus on that. Cos h 2g of z, this is going to be equal to e to the power 2g. So let's put a 2 times cos h 2g of z, that's going to be equal to e to the power 2g plus e to the power minus of 2g, right? And that is equal to, what is e to the power 2g here? That's going to be equal to e to the power I m pi times e to the power plus or minus log this. So this is going to be square root of n plus square root of n minus 1 plus square root of n 1 by square root of n plus square root of n minus 1 by multiplying by square root of n minus square root of n minus 1. The denominator becomes there is a square involved, so there is a square here, there is also a square here. This is precisely what we will be getting, which is equal to e to the power I m pi is just minus 1 to the power m, and this is just n plus n minus 1 plus 2 times something. So n plus n minus 1 is just 2 times n minus 1, and there will be a 2 times of this, and the 2 times square root of n into n minus 1 will cancel off. So this is precisely what we end up with. So what do we have? Cos h of 2g of z naught. This hence is going to be equal to minus of 1 to the power m times 2n minus 1, where 2n minus 1 is going to be an odd number now. For any integer n, 2n minus 1 is going to be an odd integer. Now if you look at the x of pi I, minus of x of pi I of cos h of 2g of z0, this is going to be equal to minus of x of pi I times minus 1 to the power m times 2n minus 1. So this is going to be 2n minus 1 times pi I into minus of 1 to the power m. Since 2n minus 1 is an odd number and cos of the minus term is not going to contribute, this is going to be equal to minus of 1, which is equal to 1. But the thing on the left is exactly equal to f of z0. So if g does intersect our set S, that means that f will take the value 1, which however is not possible, and which is a contradiction. So effectively what we have proved is that, so let's summarize what we have done. Hence, so if f is holomorphic on omega which omits 0 and 1, there exists an entire function, there exists a holomorphic function g on omega which does not have a disk, of radius 1 contained in g of omega. This is precisely what we have proved till now. So, if f is a function on some simply connected set which omits 0 and 1, this is precisely what we have. Let me now state and prove the little Picard's theorem. Little Picard's theorem states the following. If f is an entire function which omits 2 points, then f is necessarily a constant. If f is an entire function which omits 2 points, that means 2 points, there exist 2 points which do not belong to, at least 2 points which do not belong to the image of f, then f is constant, then f is a constant function. Let us give a proof of this. We have everything needed to do that. First observation is that C is a simply connected set, and whatever we just said a few minutes back, that is quite relevant for our function f as well. But before that, it could omit any 2 points, right? So, let z0 be, z0 and z1 be 2 distinct points. Which f omits. Notice that if you define, consider f of, the first observation is that we may assume without loss of generality that z0 is 0 and z1 is 1. That is the first observation. Without loss of generality, that z0 is equal to 0 and z1 is equal to 1. Why can we do this? Because otherwise, consider the function f1 of z defined to be f of z minus z0 by z1 minus z0. Notice that since f does not take the value z0, f1 never vanishes. So, f1 omits the origin, and since f does not take the value z1, f1 never takes the value 1, i.e. f1 is an entire function which omits 0 and 1. If you prove that f1 is constant, then that would also imply that f is a constant. So, we will assume without loss of generality that f is a function which omits 0 and 1. But then we now have, by the proposition we proved in the beginning of this lecture, there exists a function g such that an entire function, let me be very careful here, the function is defined on the entire omega, in that case omega here is c. So, there is an entire function g such that f is equal to minus of the exp of pi I times g of cos h g of z, cos h 2g of z. Not only is it a function which satisfies this condition, and such that there does not exist a disk of radius 1 contained in the image of G. Let us assume that f is non-constant. Now we are going to come to a contradiction. Assume f is non-constant. If f is non-constant, in particular g is also non-constant, and because g is non-constant, there exists some point z0 where its derivative does not vanish. So, let z0 be a point in C such that g prime of z0 is not equal to 0. And we will now consider a function h of z. Define this function h, which is defined as g of z plus z0 minus g of z0. What can we say about this function? Let's see what the function h satisfies. Observe that h of 0, this is equal to 0, and h prime of 0 is precisely equal to g prime at z0 by the chain rule. So, this is something which we certainly have. Now, define a new function. Define h, g, everything is taken. So, let us call it psi. Psi is defined to be the following. Before that, I am slowly progressing towards a contradiction to the Bloch's theorem. So, before we go any further, remember that h is an entire function. H is an entire function, and the image of h does not contain a disk of radius 1 either. And since the image of g does not contain a disk of radius 1, the image of this is after all composition by translations, pre-composition and post-composition by translations. So, this will also certainly not have a disk. So, that is an exercise for you. H is an entire function, and exercise. H does not contain a disk of radius 1 in its image, because if there is a disk of radius 1 sitting inside the image of h, there is also going to be a disk of radius 1 sitting inside the image of g. We now have a setup where h is an entire function which maps 0 to 0, and h prime of 0 is not equal to 0. For r, some r positive and say less than capital R, we will define the following function. Define the function psi of z to be equal to 1 by r times h of r z by h prime at 0. So, notice that whatever is there inside here, this is just multiplication by a complex number, r by h prime at 0. H prime at 0 is not equal to 0, that is being used crucially. So, r by h prime at 0 is some function which is multiplication by a constant. So, it takes 0 to 0, and again 1 by r is multiplication by, in fact, a real number. So, this makes perfect sense. Psi continues to be a function which is now in fact defined on the entire complex plane. This is a function which is in particular defined in a neighborhood of the unit disk as well. Let us see what is psi of 0. Psi of 0 is equal to 0 because each of these functions map 0 to 0. And what about psi prime at 0? That is going to be equal to r by h prime at 0. That is the chain rule is being applied, and then h prime at 0 is just going to be equal to h prime at 0, then 1 by r times z. The derivative at 0 is 1 by r, which is hence going to be equal to 1. So, we are now in the perfect setup to apply Bloch's theorem. By Bloch's theorem, the disk of radius 1 by 72 is contained in psi of the unit disk. So, let us take some w now in d0 r by 72. And if you look at w by r, that is in the disk of radius 1 by 72 around 0, that is just going to be equal to, then there exists z in d such that w by r is equal to, what is psi of z? Psi of z is going to be equal to 1 by r times h of r z by h prime at 0, which implies that w is equal to h of some z 1, or maybe z1 is already taken. Let me use z prime, where z prime belongs to some disk. Let us in particular say that it is in C. This is true for every w in d0 r by 72, which tells us that d0 r by 72 is contained in h of C in the image of C. But R was taken to be arbitrary. For R large enough, R by 72 is going to be greater than 1, and that's going to be inside the image of H. But that's a contradiction, because the moment we have a disk of radius greater than 1 sitting inside the image of H, by this exercise it will also be, there will also be some disk of radius greater than 1 sitting inside the image of G, which is a contradiction. So this is a contradiction to our assumptions, and therefore our assumption has to be false. The assumption that f is non-constant is false. This tells us that f is a constant function. And that completes the proof of the little Picard's theorem. With the conclusion of Picard's theorem, we have come to a conclusion of this course. There are multiple directions in which you could take the study of complex analysis further. One could, for example, study the Riemann mapping theorem, go into more abstract objects called Riemann surfaces, and study a generalization of the Riemann mapping theorem called the uniformization theorem. That's one direction you could take. Another direction you could take is by looking more deeper into harmonic functions and the further ramifications thereof, which is broadly called as the potential theory. One could also take up the study of conformal mappings and quasi-conformal mappings, or you could also jump into the direction of number theory, wherein you study zeta functions, prime number theorem, and such things. I hope that you have benefited from this course, and let me stop here by wishing you all the best in your future endeavors.